Maybe a couple of people are still missing, but we should probably move on. So the second session, the first speaker is Gunther Siegel from Paris, and he's talking about extragalactic magnetic fields and ultra-high energy cosmic rays.
Yeah. So thanks for inviting me. In fact, I'm not really from your community. I'm really doing something astrophysics. But recently I also got into this magnetic field questions surrounding magnetic fields and cosmic rays, but at ultra high energies. So this is a bit not so much the energy range and the environment you're interested in, but I was asked to give this talk. So basically, I'm focusing on the role of extragalactic magnetic fields in the propagation and the interpretation of data on ultra-energy cosmic rays. And I will just give you a short overview why extragalactic magnetic fields play a crucial role in this interpretation. I will discuss some signatures of structured fields, and in the end, if I have some time left, I give an example how these extragalactic fields can influence even the spectrum of the cosmic rays from individual sources. So maybe not all of you are very familiar with the ultra-energy cosmic ray spectrum at the highest energy, so I give you here this plot. These are data from 2 experiments, and I should maybe first show this transparency here. So for alpha-energy cosmic rays, how are they detected? There are 2 complementary techniques. One is the historical one, which is just by using big ground arrays of surface detectors. So imagine you have a cosmic ray interacting at the top of the atmosphere. You have a shower of secondary particles, and you have a ground array here, which is represented by these dots here. So you measure a lateral cross-section of the shower. Now, a more modern approach, in fact it's not more modern, but it's a more recent approach, is to exploit the fact that these showers excite nitrogen in the atmosphere, and that de-excitation gives rise to some emission in the blue, and this can be detected by using telescopes as photomultipliers. And usually they are arranged in this way. So this is a hemisphere of photomultiplier tubes. This looks like facets here, and that's why it's called the fly's eye technique, because it's like an insect's eye. And what you do in this case is you follow the longitudinal development of the shower. So that's why these 2 techniques are complementary. And the biggest array that has been using the ground array technique is known as the Agasa. It's a Japanese experiment which just stopped, in fact. And this one is the old fly's eye experiment. There's a next generation version of it now, which is called the high resolution fly's eye. And why I'm mentioning this? Because at the moment, in fact, the situation at the highest energies is somewhat confused, because these 2 techniques seem to give different answers for the observed spectrum. So here I show you the so-called IRIS data. So this is the high resolution fly's eye. So this is the fluorescence technique, and this is denoted by these squares and triangles here. And it seems to indicate some cutoff here in the spectrum, whereas the other experiment, the ground array technique, seems to indicate a continuation of the spectrum. In fact, even a hardening, which means a smaller fall-off. In fact, I should say, for people who are not familiar, this of course is not the flux. The flux doesn't rise, but it's the flux multiplied by E cubed. So this is still a falling spectrum, of course. Now, so basically, this is an open question. There are many open questions around this, and especially people would like to know if there is a cutoff or not, because in fact, physically, you do expect a cutoff. And this is very different from the situation you're familiar with in the galaxy. In the galaxy, you basically can neglect energy loss of cosmic rays. But here, once you go above a few times 10 to the 19 electron volts, you're susceptible to pion production. This is just reaction. Nucleon plus a CMB photon gives you another nucleon plus a pion. And the threshold for this is a few times 10 to the 19. If you plot here the interaction length as a function of energy, you get this drop here, And that in the end, above 10 to the 20 or so, this interaction or energy loss length is just 20 megaparsecs. And that means, this is physically very important because it means that whenever you see events above this energy, they cannot have come from very far. They must have originated in the backyard of our universe, so to speak. And therefore, if you think that these highest energy cosmic rays are cosmologically in origin, you would indeed expect such a cutoff. In fact, the name, so this is a very famous effect, this is called PCK cutoff, after Greiser and Kuzmin, who 1 year or so after the discovery of the CMB pointed out this loss process of ion production. Now, in fact, cutoff is a misnomer because this is not a sharp cutoff. It's not even exponential, but at least it's some drop in the spectrum. And now you have this experimental situation where either you do see a drop in one technique, and you do not see a drop in the other one. So this is really an open question. The other open question, this is more the topic of my talk here, is the distribution of this.
Sorry, but the general levels are also very different, right?
Yeah, but this
change.
Okay, maybe I should. This is a trivial problem because if you imagine that the energy normalization is off by 20%, then this corresponds to a drop of factor 2 in the level of this curve, and you see that the shape fits in this case. But what doesn't work still is to match the slopes. That still doesn't work. However, I should say that it is not so clear. There's a lot of discussion that. I have been in quite a few meetings recently, and people really discuss for hours about this. It seems a bit a strong effect here, but if you really go to the statistics, it's maybe not so bad after all. It's maybe a 2 sigma effect, and I wouldn't bet any money on that. So this could still be just a fluctuation. But nevertheless, it's something that is discussed a lot in this community.
But isn't it true that that involves quite a lot of energy interaction characteristics and things like that, things which are not very firm norms in the 10 to the 19 electron volts, etc. The one to the ground area.
I didn't understand that.
What I mean is that the interpretation of getting the flux from the measured to flux at the ground level, that involves a lot of simulation to.
Yeah.
That is not uncertainty, isn't it?
Right. This is of course true. In fact, I should say. This is a very non-trivial subject, and people are doing Monte Carlo simulations, and there are certain measures. For instance, it turns out that the density of the shower a certain distance from the core is usually proportional to the primary energy. On the other hand, especially these first few interactions, are at such a high energy, not even probed by any accelerated experiments, that you could well have some uncertainties there. So it's actually very hard to model these showers in great detail, and for instance, there are also big uncertainties in the composition. So depending on which kind of model you use, as an answer you get that we are either dominated by protons, but others predict that it could be dominantly iron. So there's a big open question there in many respects. Now, the other thing that I wanted to mention is, this is maybe with advertising, but this is this so-called Pierre Auger project, and this will be the first project which will combine these two techniques. And the nice thing is, of course, then you will see certain showers in both kinds of detectors, and then you will see if there is a systematic problem between the two or not. And in fact, this project is under construction. There is one site in Argentina, which is now, so in the end it will cover 3,000 square kilometers. These are about 1,600 ground detectors, and now they have about 400 operative. So they have already quite 1/4 or so they have already working. They're also, I think, half of the fluorescence detectors are also installed already. This is just one of these ground tanks here that you can see. And in the end, so also to give you a number here, above 10 to the 20, the flux is something like 1 per square kilometer per century. It's a really tiny flux. So now you can do a quick calculation. If it's 3,000 square kilometers, it means you get about 30 events per year above 10 to the 20. That's a reasonable rate, but remember all the former experiments have been a factor 10 smaller, so they had maybe one event per year at these energies, and that's a bit ridiculous because you have to wait for many years, and still you have not enough statistics to decide anything. So this was the main motivation for this kind of experiment. And the other problem related to this the current data situation, and this is in fact related to what I'm talking about here. Sorry, it's a bit scratched here, but this is the distribution of these ultra-energy cosmic rays. And it seems that it's completely isotropic, except maybe for some small-scale clustering, which is also hotly debated, because in fact IRS is claiming there is no clustering, and AGASA is claiming there is some clustering. It's not clear what is happening. But why is this interesting? Well, because I just told you that above these energies, the sources cannot be very far. Now, within 50 megaparsecs or so, we know that the universe is highly structured. It's not homogeneous. You have voids, you have walls, you have galaxy clusters, filaments, etc. So, at least if you have enough statistics, you would expect that the flux is not isotropic, but it's coming predominantly, for instance, from the Virgo cluster, because there are many sources. And so this is something that is also something that needs interpretation or explanation in terms of models, and it's a constraint of models. And this is also something where now what's coming in is extragalactic magnetic fields, because if you can imagine, if you have rather strong fields, then even if the source distribution is inhomogeneous, you might be able to blur things out such that things become isotropic. So one of the questions is, can we have fields that are strong enough to do this kind of blurring? And this is one of the main topics I will discuss in this talk. I will probably just skip that. Just to give you some flair of that in terms of the numbers involved. Now I'm even just talking about small deflection. So assume that you have a 1 nanogauss magnetic field, which is actually quite reasonable, maybe not in the voids, but at least say close to some filaments or so. Then over a distance of 30 megaparsecs, at 10 to the 20 electron volts, you would get a deflection of about 1 degree. This doesn't seem very big, so it means if you want to really blur out images, you need much more than a nanogauss. But on the other hand, we know that, for instance, in galaxy clusters, you can easily have fields of a microgauss or so, but of course not homogeneously. They are usually quite concentrated. So one thing we are doing in Paris, this group, is we are trying to simulate predicted distributions of cosmic rays in structured magnetic fields. But before I go into that, just to give you these numbers here roughly, one should also note that this is a very small deflection angle still, but the time delay that goes with it is actually quite substantial. Here it's about 1,000 years. So this is quite relevant, for instance, if you have bursting sources. For instance, there are models which claim that gamma ray bursts can explain these ultra-energy cosmic rays. And in this case, even such relatively weak fields would have a huge impact on what you observe in the end, because for instance, if a gamma ray burst creates a power law spectrum, then if you have such a field here, what would happen is that you have a time delay, which is a function of energy, and it's brought out a little bit by this stochastic pion production at high energies. So this is a Monte Carlo simulation which shows you the distribution of time delay versus energy. But now look at the time scale. This is, say, 100 years, but of course your experiment only lives a few years, so what you actually see is a cut through this distribution here, and that means you basically, the spectrum that you see is some bump. It's not a power law at all, it's some bump. It's almost monoenergetic, and that's very easy to understand, of course. It just means that higher energy particles, say above this level here, they have been less delayed and therefore they passed already, whereas the low energy guys didn't arrive yet because they have a bigger time delay. But this is a very strong effect. Remember, you started with a power law spectrum and you end up with some bump that's almost monoenergetic. So that means taking into account the effects of large-scale extragalactic magnetic fields might be very, very important to interpret the data. Now, so we have done since a couple of years numerical simulations, and I just show you some of the more prominent effects what can happen. In fact, you have two regimes. The first regime is when you have only small deflection. Of course, asymptotically at very high energies, you always have small deflection because the gyro-radius becomes very large. So in this case, for instance, then you have a certain deflection angle which goes like 1 over the energy. So the time delay would then be the distance propagated times the deflection angle squared. So it's almost rectilinear propagation, and you get this behavior because it's deflection angle squared. So it goes like e to minus 2. In the diffusive regime, it's quite different. This, you all know, this is just diffusion. In this case, the distance propagated is just the time times the diffusion coefficient. And so the time delay here has a different dependence on energy. It depends now how your diffusion coefficient depends on energy, but it usually doesn't go like e squared, but as some much smaller power of e, for instance, e to the 1/3, like Kolmogorov. You have seen this in one of the previous talks here. So that means actually, if you plot, for instance, the time delay as a function of energy, and you have certain parameters, like this here, for instance. So I have here a field of 3 times 10 to minus 7 Gauss over 10 megaparsecs. This is, of course, not realistic at all. Nobody of us expects a field with homogeneous properties of this size over 10 megaparsecs, but this is just as an introduction to an idealized situation where you can see qualitatively which kind of effects can happen. And then you see these two regimes. So at low energies, you have diffusion, and you see here, this is again a Monte Carlo simulation, that the dependence of the time delay on energy is much smaller. The power here is much smaller than at the highest energies where you have something like e to minus 2. So you can see this as a change of slope in this distribution, and it's also reflected in the spectrum that you would observe. So in fact, I forgot to say here I assumed that you have sources all over the place, the continuous source distribution. This is not important here, but you see also, you can get a rough idea why you get this modification of the spectrum, because at low energies, at high energies where you have no deflection, basically, you just repeat the injection spectrum. Here I neglect energy loss, so this I can do because now the distance I'm talking about 10 megaparsecs, so even pion production is not very important. So then I just, in the highest energies, I just get the same spectrum out that I put in, but at low energies, now I have this steepening. So how can I understand this? This is very simple. In this case, you can imagine now you have diffusion. So you start somewhere and you distribute your particles over some volume, V cubed, which is just what you had. Let me see. I'm not saying something wrong. Yes. So basically. So the argument is as follows. You look at a certain distance scale, E, and here we have the sources all over the place, and the point is now it takes a certain time to fill this volume, and this time is just given by the diffusion relation, so it's just d squared over the diffusion coefficient. And so basically the cosmic ray density that I will have in this volume is just given by the injection spectrum multiplied with this time scale and then multiplied by d cubed. And if I insert this, then I get a dependence which goes like the injection spectrum divided by the diffusion coefficient here. Sorry, square here. Yeah, it was square, and yes, and this is why I get a D here. But the important point is that you have now the diffusion coefficient downstairs, which has some energy dependence, and usually it grows with energy, and that means that you get a steepening of the spectrum when you go down to low energies. So this is another example how this magnetic field can influence what you get out versus what you actually put in the production spectrum. Now, Now I want to become a bit more realistic. So as I said, this is all very idealized. Here I had just, some magnetic field of a certain strength. In fact, I used the Kolmogorov spectrum here. So usually what we do is we define the magnetic field in momentum space or in k-space. We do a Fourier transform into real space in some box, and then we propagate the particles in this box, and usually the momentum distribution is given by a Kolmogorov spectrum, for instance. This is what we have done in this simulation. But this is too idealized, certainly, because it means that there is no structure in the field. It's the same everywhere. Well, it's not the same everywhere, but its statistical properties are the same everywhere. The B squared average is the same, and the spectrum is the same. Now, if you want to become a bit more realistic, then you have a highly structured situation, but then unfortunately numerically it becomes more difficult. So then what you have to do is, you have a source, for instance, somewhere, and now you have some complicated magnetic field in between, and you want to know, for instance, what really arrives at the observer, what kind of spectrum do I get at the observer, what kind of sky distribution do I get, etc. So what we do is, we propagate these particles, so we just solve the Lorentz equation for deflection, but we also take into account energy loss by pion production. And then every time one of the trajectories crosses some sphere around the observer, we register the particle, its energy, its arrival direction, etc. And then we do that often enough, and in the end we can construct any kind of distribution we want, we are interested in, for instance, the sky distribution, the total spectrum, and things like this. So basically this is what we are doing. It sounds actually very simple, but in terms of CPU time it's very demanding, because if you want to get a halfway realistic, for instance, arrival direction distribution, you have to make this sphere rather small, and then only a tiny part of your trajectories ever reach the observer. And there is no, I have discussed this with many people, and nobody had a better idea really to do that. In fact, one obvious thing which might come to mind is that you inverse this, but then this doesn't really help, because then the trajectories have to reach the source, so you have the same kind of problem. And even worse, you cannot inverse stochastic energy loss. At least I don't know how to do it. So you have to probably do something like this, and this is what we are doing at the moment at least. And one simple result that comes from this kind of simulations, I just show you here. Assume that you have only one source. In fact, this is a very ideal situation, but there have been, in the literature, there have been suggestions to explain all these alpha energy cosmic rays with just one source that is relatively nearby, within a few megaparsecs. And the question was, if you have a rather strong magnetic field, can you make it consistent with isotropy? And people had actually looked into that, but they had used analytical approximations that were not really applicable, because you're in the transition regime between rectilinear and diffusion, and you have to take into account energy loss. And then if you do it numerically, it turns out that it doesn't work. So here, for instance, we had one source at 3.4 megaparsecs. This is motivated because there is some radio galaxy there, which is Centaurus A. These are typically distance scales to the nearest radio galaxies that might be able to accelerate particles up to these energies. And then we assumed a very strong field. This is really not realistic at all. It's 0.3 microgauss. It has to go about several megaparsecs. That's certainly not the case. But you see that even in this case now, so this is, for instance, at 10 to the 19 electron volts, so EeV is 10 to the 18, so this is 10 to the 19. In fact, the sky looks very isotropic. So this is consistent with the observations, but once you go to higher energies here, it becomes too anisotropic. So in this case, for instance, your flux would be concentrated in the southern hemisphere, because Centaurus A is in the southern hemisphere, and in the north you would get almost no flux, and it's even worse, of course, at higher energies. So one corollary of these kind of simulations is that you certainly do need more than one source to explain the observations in the northern sky that are available. Now, this was still very idealized. As I said, this was very simple. Again, a box with homogeneous magnetic properties. just one source, etc., no structure in the field. Now we want to do a little bit better, and in fact this is what we have been doing the last 1 or 2 years. So in fact what we did is, I started to work with people from NPA here, with Thorsten Enslin and Francesco Miniati, because these people have a code that simulates the large-scale structure of our local universe, including magnetic fields. In fact, there are only 2 or 3 such codes on the market, and there is one other group which used another kind of code, and they reached actually different conclusions, and I will come back to that, but I just tell you roughly what we are doing here. So basically, there are these codes, which these are n-body codes, including hydrodynamics and magnetic fields. So this code, for instance, produced a 75 megaparsec cube box, which is with periodic boundary conditions. For the people who are interested in technical details, this is what the code is. This is the type of code. In fact, I am not involved in these kind of things at all, so I'm not an expert on this. What I did basically is the trajectory simulations. So basically we use these kind of boxes, and instead of these highly idealized magnetic fields, we use the fields that come from the simulation, which are highly structured. So for instance, the magnetic field distribution looks something like this. Look at the left panel. This is the magnetic field squared. These are different locations in the box. So you see that, for instance, here you have some kind of, this is a cluster here where the field goes up to a microgauss or so. This is a position close to a void here where the field is much weaker, but you have nearby regions with stronger fields here. So these are highly structured magnetic fields, and what we do now is we make a choice for the observer. For instance, we put the observer here, and then we make a hypothesis for the distribution of sources. For instance, here we assume that sources are distributed like the baryons. So for instance, there will be a high probability that you have a source here, but there will be a low probability in the void because there are not many baryons. And then basically based on this, we are doing these trajectory simulations, and then we ask several questions. For instance, do we get distributions that are consistent with isotropy? Which kind of spectra do we get, etc.? Already one result. How much time do you have?
Let's say 5 minutes.
Okay, that's why I have to be very quick actually. So maybe I skip this. So I just show you one of the simulations that we did. So this was the one that we used most often. So we have an observer here, which is close to a void, so the magnetic field at the observer is rather weak, but we have a prominent cluster nearby, which could be the Virgo cluster, and then basically we do the simulations, and one of the main results is, and I just show you this because of lack of time, and this is a very important observable, it's the average deflection angle. And just look at this here. This is the cumulative distribution of deflection angles. And you see, for instance, even above 10 to the 20 electron volts, we get rather big deflections, up to 30, 40 degrees or so. And in fact, the other simulation, there's another group which did similar things, but based on another large-scale structure code, with another treatment of the MHD. And this is the paper by Dolag et al. This is this paper here, and they get much smaller deflection angles. So they get only up to a few degrees maximum, whereas we get something like 40, 50 degrees. And the main difference, that is as far as we have figured out until now, is the magnetic fields that comes from the simulation. What you see here is the filling factor of the magnetic fields. This is in our simulation, and this is in the Dolag et al. Simulation. So you see that we have much stronger fields filling, we have fields of a certain value filling a much bigger part of the universe than Dolag et al. So for instance, we have fields here of a microgauss roughly filling 1% of the simulation volume, whereas in Dolag et al. It's just 10 to minus 6 or so. So basically, this explains probably this big difference in the deflection angles. They just have a different distribution in the magnetic field filling factors, And this is just a numerical treatment. They have an MHD code, whereas this one is, in fact, they have, as far as I know, the magnetic field itself is treated as particles. I don't know the details really, but it's a different numerical technique, and it might be just due to this difference in technique. So for now, this is an open question, but we think that basically what that means is that we don't understand enough yet the large-scale structure of the magnetic fields to reach a conclusion on typical deflection. However, this is in general a very important question, because it would be nicer, of course, if you have very small deflection, because then it's easier that you make a connection between arrival directions and sources. Because ideally you want to do something like particle astronomy. That means you look into the arrival direction and you see a source, or you can identify a source. If, however, you have deflection angles as we obtain them, then the situation is much more complicated, because then you might have to look for the sources up to a distance of 30-40 degrees in the sky, and then of course you have many more possibilities. However, I should say that even in our case, the situation might not be completely hopeless, because we also have, of course, some direction in the sky where you have very little field. So we also have lines of sight where you probably have very little deflection, but most of the directions are probably strongly influenced by the large-scale magnetic field. I also should say one last thing about this. All these simulations that I've shown you, they assume just protons. This is, of course, the simplest assumption, but as I mentioned in the beginning, it is not clear what the composition is at the highest energies. So if you have a significant iron component, then even in the other simulation, which gets only a few degrees deflection, deflection would go up by a factor 20 or so, because you have a bigger charge at the same energy. And then even in this case, deflection angles will be very big. So in any case, I think, depending a little bit on the composition and these things, but I think the role of magnetic fields, even at these ultra high energies, is not at all negligible. And this will be a very important thing to pursue, I think, once we have much more data coming in from this new experiment, which is the POJ project. Then just within 1 minute, one other thing, I used the same simulation, and in this case I looked at a single source that was located here. So this is a source which is immersed in a magnetic field of 0.1 microgauss. I think this is not unreasonable. If you have an active galaxy, it probably spills out magnetic fields, and it might well be immersed in some magnetic field like this, of this size. And I put an observer here a few megaparsecs distance. So this could be a situation, for instance, this could be Centaurus A and this could be us. Now I ask the question, how can the magnetic field influence, for instance, the spectrum that I will observe from the source? And I was surprised myself. It's a very big effect, even if the deflection angle turns out to be rather small. In fact, I don't have a plot here of the deflection angle, but in this situation it turns out to be only, if it's protons, it only turns out to be 5 or 10 degrees. So this is still affordable, but the spectrum changes dramatically. So here, this is the injection spectrum. This is just E2-2. It's a very simple spectrum. This red curve here is what you get without any magnetic field. There's hardly any change because the source is nearby, so there's not much time production. This is why the curve is very similar. Now you switch on the magnetic field. I just use the field that is shown in this plot here. I do the same simulation, and I get a completely different spectrum. Sorry, just ignore this and that because this is because of lack of time. So this is for proton primers. Now you get this spectrum. It's completely different. And the reason is because you get diffusion around the source, because around the source the fields are rather strong. So protons might diffuse a little bit until they get out, then they start to go along straight lines. This is why the total deflection in the end is not very big. But the spectrum is changed because you have diffusion there, which increases the propagated path length by a lot and makes energy loss much more important. and that's why you get a very different spectrum in the end. So my claim in this case is that even in a situation where you have only fields around the source and not much around the observer, and where the deflection could still be rather small, it could well be that the spectrum is still strongly influenced by the magnetic field. And maybe in order to avoid to go over time and just go to the conclusion slide. So I think, at least this is my personal opinion, currently I think the impact of extragalactic fields on ultra-energy cosmic ray propagation is hard to quantify. There is also a lack of numerical understanding of the evolution of the fields. I told you that there are basically two groups at the moment who are doing these trajectory simulations in boxes that were obtained from large-scale structure simulations, and we get quite different results for the deflection angles. The structure of the field can also make a big difference as compared to unstructured fields. Even the observable spectrum can depend drastically on the field structure, as I've shown you in this case where we had only one source. And I think at the moment at least that large deflections can certainly not be excluded, although we do not claim that in the end deflection will be large. It could also be small, but even in these other simulations the deflections could be large if you have a heavy component at the highest energies, which is not excluded. Then it turns also out that, in fact, the details in this spectra that I've shown here, they depend in an intrinsically unpredictable way on the magnetic field, because, in fact, it turns out that there are certain effects like magnetic lensing that depend on the details of the field that you may never know, of course. So that means, in the end, you might have to do a lot of statistics, look at different sources, such that these kind of effects average out. So you might not get this under control very much if you look at an individual source, because then you are subject to the field structure around this source that you might not know. And I think in the end, we have to move away from these highly idealized scenarios and solutions that up to now, in fact, were used in the literature, because now we know that magnetic fields most likely are very strongly structured. And in fact, one thing that we are working on is we would like to develop a kind of a general simulation tool that is kind of public, so people can use it. For instance, if they have different models for the large-scale magnetic fields, they can just use this tool and simulate what would happen. This a little bit like people are doing for the galactic cosmic rays, and we are working on that with a couple of people. So I stop just here and maybe take some questions.
All right, questions?
What would be the maximum magnetic field strength that you get no influence on the spectrum?
In the spectrum, you mean? Yeah, so the physical answer is basically, I didn't show this plot, but basically what this is, the reason why you get strong modification is because the delay time gets comparable to the energy loss time. That means you modify your energy loss. So if the delay time drops below, significantly below typical energy loss time, then your influence becomes negligible. So in this case, I would say if you decrease the field by factor 10, then in this case, which I showed you, so instead of 10 to minus 7 Gauss around the source, 10 to minus 8 Gauss, for instance, then it will be negligible, because the delay time will go down by factor 100 in this case, because it goes like p squared roughly, and then I think the spectrum will not be modified very much anymore. But it depends on the situation. I mean, it depends on the distribution of the magnetic fields. But in general, it's, I would say, qualitatively dividing the line is somewhere here. If the fields everywhere are smaller than q times 10 to minus 8, then the effect is very small. But the point is also another point that I maybe should stress is, another complication is that probably most of the sources will be in regions where you have also strong fields, because, for instance, you could imagine that your accelerators are, for instance, in the Virgo cluster, because there you have active galaxies, and in these clusters typically magnetic fields are strong. They go up to microgauss or so. If the sources are open in the voids, for instance, then of course the story would be quite different. But probably they correlate, and that makes it more important, I think.
Yeah. You mentioned with this transparency, I have a question related to this. You mentioned that the field structure near the source does affect the results. But definitely this sort of simulation cannot capture all the features of the magnetic field in a radio galaxy.
Yeah.
And there it can be even a factor of 10 higher, 10 microgauss very easily. So how important this can be, the properties of the magnetic field and accelerators in the source itself, in the radio galaxy itself.
What was the last part of the question?
So, can the result be affected by the fact that you cannot model the radio galaxy itself?
Oh yeah,
with its strong magnetic field.
Yeah, well that's what I meant when I said, in fact, the results could be intrinsically unpredictable because you cannot figure out the detailed structure of the magnetic fields around the source. And in fact, what I did, I did this kind of simulations for slightly different source positions. So I changed qualitatively some of the structure by moving the source a little bit, for instance. And the spectrum changes in a way. Here, unfortunately, I only have shown one of the cases. But it turns out that the structure of the spectrum changes significantly. And that's why I think it might be intrinsically unpredictable in such cases, because you cannot know basically enough of the details of the magnetic fields in order to pin it down.
And it's not a diffusive propagation, but rather rectilinear propagation.
Well, here it's both, right? But around the source it would be diffusive. But then once it goes out, it's more or less rectilinear, because then the field drops to, here it's about 10 to minus 11 Gauss only, so then it goes in straight lines. And this is also why you have to do Monte Carlo, because you're going from one regime to the other. So you cannot, for instance, use diffusion approximation from the source to the observer, because it breaks down once you go away from the source. So this is why in this highly structured situation, unfortunately, it's very hard to simulate, because you can do no approximations or simplifications.
So there is no random walk, everything depends on realization. You have
Right.
individual realization.
In fact, there is something that I didn't talk at all about, because there was not enough time, but what we also did is we tried to discuss what we call cosmic variance, which is due to, for instance, changes in the source positions. And it turns out that for instance, if you, we have done many other things that I didn't show you, but for instance, we calculated the autocorrelation function of alpha energy cosmic rays. And here you see the predictions. These are data. This is the Agasa data. In fact, this is a prediction. And you see here two error bars. One of them is just statistics, because you have just 57 events observed. The other one is cosmic variance. So this is due to, for instance, if you have sources in different positions or magnetic fields slightly different. And you see that here, cosmic variance often dominates, in fact. And this is exactly due to this unpredictability, because if you slightly change the environment, then then you get a different realization, and then your prediction changes. So that's another way to put it.
You had okay.
One simple question. Does the cosmic ray streaming play any role in the sense of self-excitation of waves and all of this?
This is, I don't think so, but in fact, I know too little about this self-excited waves. I think I have to think about it, but I think it's, how does that work in case of...
Well, for galactic cosmic rays, you can excite waves at the wavelength of the gyro radius, basically, and this leads to strong scattering and then diffusion.
But here probably the gyro radius is too large, because it's of the order of megaparsec. I don't know what...
Well, on these large distances, you also have like 10 megaparsec.
Yeah. Yeah, I should think about it. Actually, it's a good question. But for that, I have to understand more how this excitation mechanism works. Maybe we can discuss it.
I had actually also a couple of questions myself. First of all, you have the Centaurus A case, which would be some 3 megaparsecs away, and you had some peculiar spectrum for that.
Yeah.
So, do we have now already enough data that we could say something about it's kind of very close by. What else? Anything?
No, I don't think so, because the number. I just gave you one number, which is above 4 times 10 to the 19 electron volts.
Okay.
Agatha has seen 57 events.
Okay, so we haven't, yes.
All over the sky, over the northern sky. So now imagine you look in a certain direction. Typically you get, depending on which opening, but you get only 1 or 2 events or so. In fact, I should say that Agatha has seen these clusters, and in fact but this is really pushing things. They have tried to plot the spectrum they see in the form of clusters. Yeah, yes. Of course, this is kind of a bit ridiculous almost, because the disk is so small. But they find that the clustered component is very hard. That means the spectrum is much harder than the overall spectrum. And I was also speculating a little bit. This is actually consistent with this case, right? Because this is the spectrum you might get from a single source. It's also very hard. So maybe, but this is way too early. In fact, as I said, HIRIS has not seen any indications of clustering. So the clustering could just be statistics. At the moment, it's not clear. But of course, in the end, it would be very nice that Auger eventually will see, clusters of 10 or 20 events from the same direction. In this case, you can really start to do. You can hopefully also see individual sources, and then you can have some spectrum from individual sources. But you need a lot of statistics for that. Not even Auger might be big enough to do that in the end. So.
I think I leave the second question for the discussion, but I just tell you already, I was wondering if we can compare somehow sources that are somehow constantly accelerating, like some radio galaxy maybe, and then gamma ray burst or something else. But I mean, let's discuss that and move on now. So let's thank the speaker again. And then we have Lena Fredriksson from Stockholm, Albanova, magnetic field generation in collision with shocks, pattern, growth, and transport. And we want to get rid of this. But I'm not sure if we need to actually move it. Probably not. No, it's a little bit in the way.
This is actually a double talk. This question is going to take the second half of this presentation, and they're very closely coupled. But I'm going to present the old news, which was published very recently, but it's been underway for quite some time. I did this work along with Christian and Tors and Obi, who was my supervisor in Copenhagen. So first I just want to kind of set the stage a little bit by, this is not a truly cosmic ray dynamics talk, and neither will Christian's be, I think. But we can probably relate it to this kind of dynamics anyway. And I just want to show you a little drawing of a shock, what we mean by a shock. It is a sort of a phase transition where we have some hot plasma that is ejected or exploded into an interstellar medium or intergalactic medium even. And what we will have is a rise of temperature and density in the shock that will arise, and a phase transition that will involve changes of some of the variables that will be sort of relevant to the problem, depending on the strength of the shock. We could even have air production quantum scattering. So this is kind of what we're looking at as just a shock model. In the case of the gamma ray bursts, which we have been looking at, the shock is collisionless. It's a plasma shock, and it means that particles do not really interact if we look at them in a simple Coulomb gas picture. And the mean free paths, if we look at them as point particles just scattering off each other, are enormous, much larger than the scale of the shock. Furthermore, the particles will scatter off each other in very high correlation, so that if one particle moves to scatter another one, a whole ensemble of particles around this pair will also be somehow influenced by the collisions, or the point particle collision. The way that this can be remedied, that the mean free paths can actually be shortened so that the shock does arise and the particles interact to produce this phase transition, is through an electromagnetic field. And one thing that's very important is, of course, that if some explosion produces a shock moving at very high Lorentz factors, we have a particle ensemble interacting with the interstellar medium, which is in that frame very anisotropic particle distribution. So basically have a delta point function in velocity space that just is interacting with stationary gas. So it's not fluid. The fluid picture becomes less valid in these cases. So in the context of afterglows, this is how we looked at these shocks, and the simulations that I will show in a moment should be related to physical quantities that are relevant to gamma ray burst afterglows. Shortly, this is one of the only observational evidences. I think it's the only really good case of a spectrum of an afterglow that shows synchrotron radiation and some cooling regions or cooling intervals in the frequency scale of afterglow. And it will require, current theories require a strong magnetic field present in this case to explain this sort of spectrum. Also, a power law distributed electron distribution will be needed, or at least some sort of efficient acceleration and heating of the particles is needed to produce this sort of spectrum. Again, this will also require bulk Lorentz factors of the order 10 or maybe 100. At least it is quite relativistic in such a shock. We also need electric fields, and radiation is also part of this picture. Anyway, so presently we still are beginning to change our view of such a collision-less shock. But until now, in a fluid picture, we've parameterized the magnetic field and the energy content in the magnetic field and in the radiating particle ensemble into two parameters, and they are sort of devised as one just says. We know we have to have magnetic field. We know we have to have a hot particle, radiating particle ensemble. So we make two parameters. First of all, as you will see from this talk into the next one, these two parameters are completely coupled. I mean, they are part of the same process, basically. The challenges connected with explaining a gamma ray burst afterglow is connected with explaining the two parameters. How do you get the magnetic field, and how do you get the particles heated and accelerated to produce this radiation that we just saw? And there's been a number of possible attempts to explain the magnetic field by have simple compression of the ISM from a shock wave that should, or explosion that should hit the ISM and simply compress the magnetic field. It should be it could have been progenitor born, but this is known by many orders of magnitude, or at least a reasonable number of orders of magnitude. And if there's any other way to produce this field, I haven't heard of any others, but if you have, please say so. Anyway, and also we do have problems with heating the electrons and partitioning the energy between ions and electrons. The ions are carrying a lot of bulk momentum in this kind of shock. So that's the questions we're basically addressing now, is how to create this magnetic field and how the particles are accelerated to produce the radiation that we want. So we try to do some simulations using a particle and cell model that basically solves Maxwell's equations on a grid, and a simple Cartesian grid, and then we move particles around that possess charge. We move them around by the Lorentz force, and that's basically all we do. It's a smooth particle simulation, and in this sense, particles do not interact except with each other, except through the electromagnetic field. And we kind of sort of are in a regime where all analytical results from loss of Boltzmann plasma dynamics are valid. But I will not get into it. The experimental setup is shock stationary frame of reference. So this is the computational domain, and if we're sitting in a rest frame of the shock, we will move into the interstellar medium at very high Lorentz factor, and then somehow in this region the plasma will be shocked and move at lower velocity and higher pressure out the other end of the box. And it's a rather large simulation, since we successfully got some high power computers to parallelize this pretty well. So, one more thing, boundary conditions are radiating or absorbing, so that if there's any radiation or Poynting flux, it will move out of the box to not influence the simulation.
Excuse me, what's the ratio between ion and electron mass so low?
Because if we want to resolve both the dynamics of ions and electrons in a reasonable time, due to the very costly computations, we need to reduce this mass relation or mass ratio. Otherwise, we'd have to run the simulation for at least 100 times more, longer than we have to do now. So we
Can you contrast the result of
that's always a good question. But we have actually done a few scalings of the mass ratio, and the result seems to be scaling accordingly to this. So, but of course, I mean, as there's dispersion in the code, and there's all kinds of things happening that can limit the validity of the results. So the result of running the simulation, I will just show you first the early results which we presented at the gamma ray, what was it, jets and beams and gamma ray bursts in 2002 here. I would like to show you how the streaming, this is one of the early simulations, but we have the shock front here, and the initial condition is a density jump across this interface, and the velocity where we have low density and high density, and a velocity jump with high velocity and low velocity streams. So it's basically in the frame of the shock. And what you see is first the electrons will reduce the instability of two-string instability, and then perturb the ions to do the same. So it's actually these are an electron stream, and this is an ion stream. And the scales are accordingly larger for the ion masses because there's much more inertia hidden in the ion. Scaling down this to compare with the simulation snapshot that I have here, that's about right. So this is the electron instability. This is a recent run, which was also used for the paper that was published. The electron instability is here, so they form sort of current channels in this two-stream instability. Perturb the ions that then take over and filament into current channel networks that will where the current channels will merge. And from simple electromagnetic, they simply induce a magnetic field due to the fact that they are as wires. Here we have cut through the computational volume at where the electrons dominate this instability and current channel production, and where the ions are dominating the dynamics. As we see in the beginning, only the electrons are forming very small channel network, and the ions are basically not responding because they're heavy, just kind of moving through the plasma and making sure that we still have momentum in the plasma. And in the ion regime, we see much larger structures, and actually then the electrons that are now starting to feel the potential of the ion channels will try to shield these to make things to shield this potential, and this will sustain the current channels for a much longer time than has originally been thought. Actually, the original linear theories predict that this instability will saturate when the ion skin depth is reached for these structures. So, but in fact, this image here has a number of ion skin depths across here. So the instability certainly keeps growing beyond these ions in the ion skin depth, and this is due to this nonlinear interaction between the two ensembles. So the shielding of the ion channels. Furthermore, this is a snapshot of the transverse magnetic field structure. It's very strong here. As you can see, we have this toroidal field, what do you call it? Axisymmetric field around these current channels. And this is also this is a transverse magnetic field, but also a transverse electric field will arise, which is directly proportional to the strength of the magnetic field, because the ion channels, these filaments of ion current, will produce electrostatic potential, and this Christian will tell you more about. The interesting thing about this is the fact that, I'm sorry for not having made a recording of this, but we have across here, I think something like, 8 ion skin depths, I think it is, and along the scale is the same as the scale in the simulation. So we have plenty of ion skin depths resolved. What's interesting about this is the fact that once the filamentation instability sort of has developed, then the magnetic field will be transported down through the plasma at some velocity intermediate of the streaming velocity and zero. So it will percolate the shock front slowly and magnetize a very, very deep region of the shock, according to this simulation. back to the slides here. You can see that we've made a Fourier spectrum of the transverse magnetic field structure, and it starts out with the linear growth in LIGO instability, two-string instability, and then in fact it grows to our system scale, and we cannot follow this, of course, the structure growth beyond the system scale. But what is very interesting is actually the power law that these field structures exhibit. One more thing is that the B field is patchy and it's playing parallel with the shock, simply because of the fact that all the spinning is perpendicular to the shock, so you get the magnetic field structures in the plane directly. But this is actually a very important result, and this also means that the ion current channel strength will be completely proportional to the Fourier spectrum of the B field. Field generation efficiency that is needed to explain the spectra that I showed you before. It's around a few percent. The literature cites a few percent magnetic field energy of the total energy in the stream, and this is indeed what we see. There's too many graphs in this picture, but this is epsilon b. This is epsilon b at 2 times, and what we reach we're in the range of a few percent of magnetic field energy density. So we do in fact see that there is produced a strong magnetic field. Shortly, I can say that also this means that the turbulent field will eventually isotropize the particle distribution from being a delta function in the c direction to spread to the whole velocity space. And furthermore, the charge separation and electric fields will spread this sphere, velocity sphere, so that it thermalizes, or at least accelerates particles to fill this velocity sphere. But Tyson will also tell you more about this. And finally, the B and E fields are no longer separable and very nice as they are in MHD simulations. So that's kind of important to realize that we do actually need electromagnetic simulations, and I believe to solve this problem, and so I believe that justifies the model. Here we see the shock interface is here. Approximately, this is the streaming direction, and very fast the electrons are accelerated and thermalized to try and shield the ion channels. But basically, the very strong momentum, this is basically the strength of the momentum of the ensembles. The ions will just keep going because they're not affected by the fields in the same way. This is probably could scale with the mass ratio such that the ions would be even less affected if we used realistic mass ratios. Also, in the transverse direction, particles are deflected due to the existence of the magnetic field and the electrostatic potential from the current channels. And this doesn't tell you very much, except that at least the electrons are heated, and therefore they have energy that they can radiate if there is caught in some strong magnetic field. So that's all I really want to say. Magnetic fields are generated quite naturally, probably, in collisionless shocks, if we accept the existence of collisionless shocks as a possible entity. field structures exhibit parallel scaling, as you saw. Beyond this linear, the limit of the linear theory prediction of the skin depth limit, and field structures will be transported deep into the shock region. So those are the main things. And the mass asymmetry is important for this because if we had a pair plasma, the ions and the electrons up to the same mass would now not be able to, would shield each other perfectly and smear everything out. So it wouldn't be a strong effect in the case of a pair plasma as it is in the case of the ion electron plasma. So this mass asymmetry is essential, but and how it scales with the ratio, that is probably very linear with the ratio. So at least the strength of the field. Not the strength of the field, but the scaling of these structures. Particle acceleration is completely intertwined with field generation, and this is what Preston is going to talk about in 2 minutes. And these two parameters, I hope we finally can show that they are part of the same process. And I think I want to leave the stage to Preston. So that's all.
So, questions? Okay.
Coming back to this question earlier, I mean, you just mentioned now that you think that it will linearly with a mass ratio, but I'm just wondering if there is no possibility to excite waves, and that would maybe depend on the driver radius or something in a B field, and that would, I mean, depend on the mass, and so that there could be some nonlinear interaction between waves and magnetic fields, and that was something that's going to happen.
Yes, it will happen. The thing is, this simulation is limited in fact in the sense that these are smooth particles, and we cannot resolve, for example, synchrotron radiation, and I mean very high frequency radiation, or high frequency electrostatic waves, to a point where we can resolve any very, very microscale plasma physics. But the dispersive properties of the code, if you accept things such as Landau damping and these sort of plasma physical effects that could erase all these field structures, then they can be modeled by the dispersion of the code. So if you accept one, you can sort of say that the model will have that taken into effect. But I mean, it's of course, it's the best we can do right now. But there should be probably included some sort of radiation, field that could influence this in another way than just through the particles.
Yeah, I mean, since you were treating things at a really fundamental level of particle and of fields, and you would also have to consider particle wave interaction, and that could be non-linear. And that would depend, I thought, also on the mass of the various particles.
Yes, it will depend on the mass ratio. I think we should do more extensive.
So something like non-linear lambda band wouldn't help you. I mean, it would be an extra process, but it would sort of erase the effect.
Erase which?
Then you have wave-particle interactions. And
you have wave-particle interactions.
Yeah, but the wavelengths must somehow depend on the
mass ratio.
Yeah.
It will. But we cannot resolve better than this at the moment. So we trust that these plasma physical effects will be scaling parallelly to depending on the mass spectrum, so both effects might be behaving in the same way, but it's a smooth particle situation.
About and we are doing studies with now that the mass spectrum 4, 8, 16,
Yeah.
and so to see if it scales linear or something like that. So we should find out eventually.
Okay, so let's thank the speaker again. So we have then Christian from Copenhagen, I guess.
Yes.
Non-thermic power law acceleration in astrophysical plasma shocks. And this is the last talk today. And while you are doing this, I remind you that if you haven't discussed it about your bills, you should do it tomorrow morning. Otherwise you don't get your money back.
Okay. My name is Christian Hildal, and the title of this talk is Non-thermic power law acceleration in astrophysical plasma shocks. Before we really start, I should probably also, as other speakers, try to justify why this could be relevant to you. As we heard today, often you inject your cosmic rays from supernovas and gamma ray bursts, and normally you wave your finger hands and say, I accelerate the particles in the shocks. What we really do not know is the microphysics of these shocks when you have a relativistic regime with very few collisions or no collisions. So we try just to, as Jacob explained, to smash shocks together and pass it together and see what happens, pure physics. And the result is based on a paper that was on the archive yesterday, so if it's not relevant to you, at least it's brand new. What we are dealing with is, we have in our case study is a gamma ray burst. So we have a burst, which we don't know very much about, but the burst will inject some matter, just like supernova. And this matter will interact with the interstellar medium. And what we focus on is zooming on the shock from itself. The observed radiation from these gamma ray burst afterglows have very clear synchrotron fingerprints, and there are clear evidence of power law electron distributions. So that moves the question to how do you get these power laws? And right now, the general accepted scenario is that you have a recursive process. That's one of them is that you accelerate the electrons across the shock boundary upstream downstream. And basically what we have is you take a thermal population of plasma, inject into another plasma, and then you assume that above some threshold energy, these become collisionless and will only interact with magnetic fields, electromagnetic field, and they can be accelerated through thermal acceleration to a power law tail up here. But there are some problems with this, and one of the problems that was recently pointed out by Brady and Barry is that yes, you can create this high energy power law tail, but observations are more compatible with something like this, where you don't have a small fraction accelerated, but you have almost the whole population accelerated to a power law. And in thermal acceleration, you assume that you will compression your turbulent magnetic fields from upstream to downstream, but if we remove the MHD approximation by disturbing the population function of particles, who knows what happens to this turbulence? Secondly, in Monte Carlo simulation, as Jacob explained, you normally have to work with compression of the magnetic fields. But the gamma ray burst, this is still order of magnitude too weak, so you have to amplify this field. And who knows what happens if you add an amplifying process to this scenario? What happens to your turbulence? I mean, it could alter the nature of the magnetic fields over the shock boundary. And problem 3 is that Monte Carlo simulation of this thermal acceleration normally yields a pretty universal slope of electron energies, whereas observations has a larger variety observations of gamma ray burst and afterglows. And there's if not a contradiction, then there's a sign that the wave acceleration picture might be too simple to make observations. So the consequence is that you have the observations from a gamma ray burst, which is basically a punch source. You want to infer what's going on, what the environment of the burst is through observations, and you infer some kind of black box where you make a lot of assumptions about the physics, and making assumptions you might just miss the point of what's really going on at the burst. So we have been doing particle cell simulations, and as Jakob explained, the variable two-string instability is capable of producing magnetic fields strong enough to match observations. And another point is that these magnetic fields in the shock region is power distributed spatially. So the acceleration scenario that we suggest propose is that you have these current channels that Jakob showed you with a strong ion current channel here. This is very schematic, of course. And you have the electron inside the divide cylinder of this current channel. And the E field from the current channel will accelerate the electron, and the induced magnetic field from the current channel will deflect it. And so we gain a high energy in here, and we'll come out reversing the process, losing its energy again, and be trapped in a potential field inside this current channel. And this is from a simulation. It's the same as the schematic view, just from real life or for simulation. Here you have the current channel, and these are electron paths. And the dark color of the electron path means it's a low energy, and the bright color of the electron path means high energy. And you see low energy, high energy, low energy, high energy. Also, you see that the electrons are pretty much trapped inside this current channel. And this is, from our point of view, a very important point. But this means that all the high energy electrons will be trapped inside the current channels, which means in turn that no high energy particles can be found outside the current channels, and are thus they cannot be subject to recursive acceleration, just as you expect in a wave acceleration, where you keep adding to the energy in a lot of steps. So this gives us a power law as we want. Well, this is the graph that Jakob showed you. It basically says that the current filament structures are power law distributed in the space very nicely. Also, we have found that we are taking for each electron, we have measured how strong is the local current channel, ion current channel value, and we have plotted this in a scatter plot here with the electron energies here and corresponding ion current channel values here. And you see there is a correlation, at least for astronomers, I would call this a correlation. And taking the average of this, you get this curve. I'm going to return, this we'll try to fit the power law. I'm going to return to why this is not the best in the world, but adding these two pieces of information together explains why when you plot the particle energies histogram, you get a nice power law for the high energy parts with a cutoff off here. And in this case, the slope is, of this power law is 2.7. But what we need to do now is to find out how this index changes with adjusting the parameters of the simulation setup. The power law here is between a relativistic gamma of 10 and 40. And in this range, 10 to 40, or 10 to 30, there's a nice power law in this average function. The reason why it's lower up here is that when the ion current channels form, there might be some low energy electrons there already. So they are trapped inside without getting any more energy. That's one you see down here. So they can drag the average down. But also outside the current channels, you still have some heating. You get a thermal component to the electrons outside the current channels, which means you have a little high energy out here, which will drag the average up. Taking all the things into account, you can get the power of it to be nicer, but this is raw data. So the speculations. Returning to the ion electron mass ratio, I might just add that since we have ion current channels shielded by electrons, makes it pretty stable because the magnetic field is outside the current channels. So the ions travel inside a no magnetic field band and are shielded by electrons. By reducing the mass of electrons, you might just shield it even better, which makes it even more stable, but this is speculation. But using a real mass ratio, we can scale up and say we can get electron energies up to 5 electron volts, which is not quite enough yet to mass observations, but if we had even larger computers, we could make the simulation larger and we could expect to be larger current channels, which would give us high energies. This leads me to the second point. The ions in simulations are only 5 to 10% thermalized when they exit the box again in the downstream end. And this means that the process is not finished yet, so you get high energies by making larger simulations. And finally, when ions finally thermalizes, there are no longer anything to support the generated magnetic fields, and one can suspect that this field might dissipate away. And this means that for the outlet location, you get your acceleration and your radiation from a very thin layer. But this is true speculation. That's it. And not to delay your wine and snack and beer too long, I'll jump to the conclusions. The magnetic field generation, as explained by Jakob, and the power law acceleration of particles are highly connected processes in the case where you have weak or no initial magnetic fields and collide two plasmas. And secondly, the acceleration of electrons are instantaneously and is local, and this implies that the radiation you receive from the shock would be very local oriented, which means it will be a good handle on the local physics, plasma physics in the shock, observed shock region. And also the fact that it's local and they lose energy again after traveling through the ion channel means that there's not so much room for film acceleration where you keep adding a little energy each time. So before I finish, I'll just give you a little movie, and it's not very scientific, just pure eye candy. It's just a zoom through the box partner with a simulation tool. Visualization tool. This is the ion pure filaments down through the box. Thank you.
So questions? Okay.
I'm just wondering how you actually avoid first order thermal acceleration in this process. I mean, you told us a nice process that also works to produce the power distribution, but it's still a shock wave, and so you would also, assume that you have some first order thermal acceleration as the particles get reflected backwards to the upstream medium and cross it again.
If that was the case, we would see.
Why doesn't it happen?
Yeah, I mean, this is a simulation that takes the maximum equation and the momentum equation, so there are very few approximations. So I guess we should see them outside the current channels then, with getting higher and higher energy. We don't see them, but so to answer your question, I can't answer them, I don't see them.
But you don't see them because you have no possibility to reflect them backwards in the upstream medium?
But one thing is that the shock is not fully thermalized. What you see is here is only part of the shock transition region. But as I said, that is when if you could zoom out and see the whole shock and the upstream and downstream region, there will only be a magnetic field inside the transition region. So when they finish that they cannot backscatter again, because in the gamma ray burst case, the magnetic field is too weak outside and afterwards to match the observations. The ISM magnetic field is too weak to match observations.
What's that? I mean, they would produce their own waves and be scattered backwards like an ordinary supernova random shock.
So you should suggest that there will be MHD states if you zoom out enough. Yeah.
Well, I would assume.
Could be, but again, the radiation we want to see is from a very strong magnetic field. That's only in the transition region you have that. So, but it's speculation.
What else you wanted to say?
No, it was a comment. Okay.
Yeah, I didn't have time to find the paper, but there is a paper recently, my observations in the paper is strongly thermoaccelerated work. It's one of the best observed supernova remnants, where the edge is so sharp that it conflicts with firm acceleration with a factor of 10. If you had firm acceleration, you would see particles, the ones that are to be scattered outside, and they would emit some radiation in the field outside, and they don't. So that's an empirical strong clue against diffuse shock.
That's one case. You say you have observed, well, there is an observation of one case where...
It's the best observed case. That's why there's one case. It's the one supernova remnant that Chandra has observed the best. And that gives a factor of 10.
But you're not going to say that Fermi acceleration doesn't work at all. So.
Well, it's amazing. There's a mechanism that has been around for decades, but it's based on assumptions. Nobody has shown from first principles that it works. It's based on assuming that you have scattering.
But I remember there have been numerical simulations at least that show that it works. I mean, especially for interplanetary shock waves, it gave very good agreement years ago with what people measured as a magnetic field behind the shock, etc.
But what you mean here when you say it works is that you can match observations. And that doesn't constitute proof. It just shows that you can get one answer one way or you can get another way. And the fact that it matches is not proof.
No, it's the same in this process. You just match observations.
No, this is ab initio. This is from first principles. So this is a shock where you should see firm acceleration if it was there.
Can I just add that all these simulations that you talk about that shows that firm acceleration works, these are not first principle simulations. These are Monte Carlo simulations where you have one population that can sustain your turbulent field, you have one population that can be accelerated. You don't consider that it actually might interact. So there are assumptions also in these simulations, so they might not be right.
Well, as far as I remember, these simulations by Jones et al., or by Scholler et al., they show, I mean, they even try to simulate particle injection, and they show that you actually can get a polar distribution if you do that. So, I don't quite see why the Fermi mechanism should be ruled out.
It might work, but this also works. So. I mean, but again, these simulations are, I stress this, the other simulations talk about also recently by Niemitz and Ostrowski. They take part of stuff right, but they separate the two populations. They don't make them interact with each other. I mean, if you need a power law population that is at least comparable to the background thermal population as observations suggest, definitely they're gonna change the ambient magnetic field to use as your Fermi agent. But this is not included in these simulations.
Well, recent simulations, I recall, a recent paper by Bell and Luczek, they propose that you actually increase the upstream magnetic field by cosmic ray streaming, and that would give you a higher magnetic field, and that would actually allow you to reach higher maximum momenta in the thermal acceleration process. And that seems to at least be, well, that's at least one possibility to explain the spectrum beyond the knee. It's not the only one, as we shall see. But so there is, I mean, what I was saying is that there is a possibility to actually also increase the magnetic field upstream of the shock, just by having particles drifting upstream and by exciting waves or strong turbulence there. that would give you then a higher magnetic field for your thermal acceleration process.
Yeah, but I'm merely presenting the first step on a new path, so might be wrong, might be right, but
you mentioned electron energies up to 5 GeVs under the talk, right? With a realistic mass, so that's gamma factor of 24. And then you said something, referred to some observations, but I didn't get into. I mean, what observations do you mean? Singleton radiation or inverse?
I mean that the observations of from the gamma ray burst afterglows indicates that electrons with even higher energies than 5 GeV can be found. And so we need to explain that, of course. I should mention that the injection here, the collision speed of the two plasmas are gamma equals 15 here. So that's how much energy we pump into the process.
So maybe we close this session and start the next one. And thank Christian here.
So I think the discussions that have gone on so far have made my job quite easy for the half hour we had before being refined, because there were three quite vigorous discussions arising from earlier talks that were cut short and specifically referred to now. So if I remind you what they were, the first was to do with the radio distribution in the galaxy, of the distribution of supernova versus the distribution of gamma ray emission, and then Anwar also mentioned the radio distribution of magnetic field. And these things seem to be in some conflict, and so I put these radio distributions together in a meaningful way. The second thing that was discussion that was cut short was whether the diffusion coefficients, they call it K for cosmic rays in simulations and modelling, whether this was dependent on the magnetic field at all, and what importance this had to the results of the simulations. And the third thing that was not even discussed at all, but was immediately said maybe we could discuss that later, is whether modelling can distinguish the sources of the ultra-high energy cosmic rays from point sources like gamma ray bursts and diffuse emission, and whether the modelling that was described earlier leads to a way to separate these two types of origins. So these three discussions were cut short, got half an hour or so to continue. Maybe starting with the earliest one, if anybody wants to take off again. I know that they basically seem to have got to a state where the conflict between the gamma rays and the supernova was proposed to be either to do with the way that the gas density distribution is inferred from carbon dioxide observations, or whether there was a radial profile of galactic wind strength. I think this is what my understanding was where that was left. And we haven't really touched at all about the apparent conflict between the supernova distribution and magnetic field if there's equipartitions supposed to hold. So,
May I just make it short on this little bit, just to cover the memory so that people can talk. If you take for magnetic field the deconvolution of Bohr et al. Of the signal in the city, in the galaxy, then the difference in the cosmic magnetic field strengths between, say, 3 kiloparsecs and 10 kiloparsecs is a factor of 5. The field of the inner galaxy is 5 times stronger than in the Sun. If there is an equipartition between cosmic rays and magnetic field, you might expect the enhancement by a factor of 25 in cosmic ray number density in the inner galaxy and here. Even if you now take the supernova distribution at the source, it orders of magnitude away from the factor of 25. Does this mean that the gradient in cosmic ray number density is much shallower, much lower, the radial gradient in the Milky Way than the gradient in this way, with the implication that there is no energy competition between cosmic rays and magnetic fields? with further implication that this keystone, cornerstone of radial astronomy, just doesn't. So, where we are now in this system, I don't know what I'm saying is completely wrong, and I make a silly and trivial mistake somewhere that this correct and this dreadful. Or hundreds of people who use computational assumptions in their estimates resulting from cyclotron, that are all of them are wrong.
Well, they do it because they always say they do it because they have I never understood why they should be.
But first, do we agree that there is no contradiction from this evidence? That this indicates there is no contradiction. First, yes or no?
I don't think you could say. How can you say that? I don't think. I mean, even if they're the same distribution, that could be by chance.
Nothing, of course, our talk on Saturday relies on the partition.
Nothing relies on nothing in the data analysis.
Well, I would say you have a partition wants to give the system enough time to reach the state of minimum energy. Then you have a partition. But if you have a really dynamic ISM where things happen all the time with explosions, then of course the equipartition should not hold. Why should it hold in such a case? So I would say it depends really on...
Well, the nuclear energy confinement time is just nothing, just 10 megayears at most. It's one correlation time per solar turbulence. From the viewpoint of cosmos magnetic fields, it's a minor time. It's just 1/10. So cosmic rays are very tightly confined in the galaxy. They have lots of time to come to any steady state.
Well, that's only true in a global sense. I mean, that they have a...
But you have deviations in a global sense. You have global deviations.
No, but I'm saying they could actually leave locally without really disturbing any of the numbers here. So if you have locally a high cosmic ray production rate, these cosmic rays could actually flow out of the halo together with gas and just go off.
Well, there is an idea related to particle instability. Namely, if you have a horizontal magnetic field, then you can even pump the cosmic rays. Then at some moment the magnetic field line breaks somehow, but releasing the excess of cosmic rays. So this is a kind of valve mechanism. So you cannot accumulate too much of cosmic rays, because if it is too much, then it opens and then closes again.
This one, I think there is much better.
Okay.
Because you are all
wait a minute.
Regulated system.
Wait a minute. And then maybe there is an analogy between this effect and, for example, the temperature or energy contents of flux loops in the solar corona. If they are closed, they are hotter. If they are open, they are colder. Or at least the energy emission is much weaker from the open field lines. Because the gas is free, the hot component is free to escape along the open field lines. So maybe this is the same, and we cannot expect the same equipartition in the open field lines and in the closed field lines.
It's fine. But still, you know, when talking about open or closed field lines in application to the solar medium, they're all handled down to very small scales. So there are no straight magnetic lines in the ISM. Forget it, they're tangled down to the scales of a fraction of parts.
No, but
in this sense, they're never open. There is never a magnetic line which extends from z equal to 0 to 1 kiloparsec.
Yes, there is.
No? Not in reality.
If
you start averaging, but cosmic rays don't average anything. They just follow real magnetic line, which is tangled very significantly.
If you have a particle loop situation,
yeah, of course.
No,
but I think that
it's only on average. And cosmic ray electrons, with their larger radius, they carry about average amplitudes only on average. But every single magnetic line is strongly tangled because the turbulent magnetic field is stronger or at least as strong as the regular large scale.
Well, that's because you have a really powerful source inside the disk. I mean, this really doesn't care about the magnetic field at all. The magnetic field is just taken away with the general outflow. Even if you have large loops, or whatever height you have, and we have done simulations that...
But the vegetable diffusion never show anything of that sort.
Sorry?
What we do know, roughly, is what is the jet geometry for magnetic field is in equilibrium. It is not that all.
Yes,
It is not.
it's very
No,
difficult
so it quite many details. You have single emission from distance of 100 parsecs, 500 parsecs, polarized emission different wavelengths, samples different lengths, optical polarization samples in 500 parsecs. You have a lot of information. And there are no indications that all magnetic lines look like trees in a forest. No, all pointing upwards, allowing cosmic ray particles to escape free. Not that. Horizontal field does do.
Well, they have to escape somehow.
Well, I put ahead of all these standard models where they escape diffusively with diffusion coefficient 10 to the 28 centimeters squared per second, and so on and so on. All this standard picture, which then leads to a different competition.
For why I see why it does. And we have this huge halo, the cosmic rays we see that come from almost a huge region, come from so what I do with partitioning, because it's like a huge box, it's almost like the old box in some ways.
Well, the box with no uniform magnetic field and a uniform distribution of sources,
Right,
right?
like that it doesn't really matter, it's just the diffusion coefficient.
This depends on what I think.
In some way.
But you're giving me a second question now, maybe you should remind everybody of 10 minutes on that one already.
Even if you had a very low magnetic field, you could still get diffusion. Because the rate of gyrations is so small anyway, even with 10 to the minus 7, it doesn't really depend on the value of the magnetic field anyway. It just depends on the diffusion coefficient.
The last observation of H-on galaxies shows that there is X shape of magnetic field, and also magnetic field which goes up to the halo. So more and more.
Average over 3 kiloparsec scale. But locally, this was 1 parsec.
Yeah,
You can look as elsewhere. If you take a microscope and look at those galaxies with X shapes, you will never see those X shapes. Because the turbulent field exceeds the large scale field, at least by a factor of 50%. The ratio of energy is over 3.
But there's no contradiction. I mean, you have really tangled fields on small scales, and you can have on large scales, you can have these quasi-open field lines. There's no contradiction.
and it is observed now.
Not many cases have been observed. They're a small number that people really like because you see these nice vertical fields. But most of the galaxies that John, you just see
but
the fields in
problem
this.
of resolution now.
Can be, yeah.
It's an observation
It's only
time.
problem
Can be,
of-
right? Resolution should have very long observation times to really see weak fields in the halo.
Yeah, I understand.
I made calculations in such fields which goes up, following down, but when we take beam which is quite large, everything is small and keep up to observation of effects, but it's quite well. So it's this problem of resolution.
So how it works means that this estimate, this curve with magnetic field, which Ember showed there, it is based on the competition assumption. Right? This data convolution of Boyer account is based on the competition. Now, if you abandon the competition, we assume that cosmic ray number this is smaller within a galaxy. The curve with magnetic field will be even steeper.
No, what I showed was mine, what we did on the magnetic field, had nothing to do with it.
Yes.
Took the electrons from gamma rays, and then took the synchrotron, and that gave me the field. No competition in it at all.
You always look very similar to this Boyman that Albert was talking about.
Sorry?
What you derive for the magnetic field from that looks very similar to what Boyman and Al derived regular.
This is the same.
But this cannot be true then. Because if you have a competition, then there must be a square root relation on the
Made by chance it is the same as well. The Boyman is quite old, and they didn't use gamma rays at all.
Of course. It's just symmetry and competition assumption. I compared with the Osborne price, which is not very different. Okay, so they have a big peak or something. And they didn't use it. Very small.
Then the calculations don't use. The ends do not use. If there is a competition, the concentrated number base must vary the square of magnetic field strength at this structure, which is by the order of magnitude. Magnetic field strength varies by a factor of 5. Concentrated number base must vary by a factor of 25. It does not. So what's wrong?
Well, you don't have a hydrostatic equilibrium of the interstellar medium, and
it's unimportant. Why like this?
No, because you have sources that are very powerful, like supernova explosions, and they can even be clustered and creating more powerful sources like superbubbles, and then all these equipartition arguments have no sense.
Oh, no, this is okay. First, let's work. If there is no equipartition, this means that cosmic ray number density will be even higher in negative, so lower than equipartition limits.
It can vary locally, that's what I would say. So equipartition is a convenient assumption if you don't have anything else at hand. That's what you usually do. Or if the system has enough time to settle into some sort of equilibrium, which in some cases it might have, or in some regions it might be a good assumption, and in other regions it might not. I think that's all about it. I wouldn't really give too much significance to really require a global interstellar medium model that equipartition holds on all scales. I think that's not making much sense.
Is it a conspiracy that the energy density of cosmic rays, since the 1 electron volt per cubic centimeter, is equal to the energy density of magnetic field? Or it's just the wrong scale? Or that
It's a coincidence.
Too many coincidences.
Why? A-class theory statistics. Combine many coincidences. It's also equal to the CMB. Is that a coincidence? Maybe that's not a coincidence. Or the starlight is also 1 eV, but I can't see that has any relation to the magnetic field. A lot of things are 1 eV.
I mean, in some sense, these processes are uncoupled. I think that's what this equipartition argument really tells you, that you must have a strong coupling between magnetic field, between thermal motions, between kinetic motions, between cosmic rays, between maybe starlight, because all the sources are young stellar objects, I mean massive stars in some sense. So there must be some close connection. But that this really holds on a global scale, I think nobody can tell, really, for sure.
At what scales does it hold?
Well, at scales of kiloparsec, or 10 kiloparsecs, or 15 kiloparsecs.
So it cannot hold at the scales less than the diffusion rate of cosmic rays. The scales less than 12 parsecs. There can be no partition at those small scales. You have a huge peak in magnetic field at the scale of one blob of the size of 100 parsecs. By no means, diffusion length is a lot larger than that. Cosmic rays will neglect this. So there can be no partition at scales less than 1 12 parsec. Now we are saying that there can be no partition at scales of the order of 10 12 parsecs. That there is no room for partition at all. But then, it's again, well, perhaps I'm too conservative, but this equipartition assumption, which has been applied for decades, never, I think never, has led to any unreasonable results. It consistently leads to some quite reasonable results for all sorts of objects, from exotic objects to standard objects. So it does work in many various circumstances. So again, it's not a proof, but if you abandon it, you have to replace it by some other assumption, equally successful. Can you offer it? Can you tell me how long you feel if cosmic ray number bases are related? If they are unrelated, how, given an object, you can estimate the cosmic ray content of this object? If not with the equipartition, it's right? More or less. Without equipartition, what should we do?
Our galaxy is no problem because we have nice camera observations. External galaxies, we don't yet. We will see. I mean, with glass you can probably see M31 cameras, and then you can do the whole calculation. So, obviously these...
Well, yes, so you can observe, but you should understand why the cosmic ray number is as it is. Okay, as implied by numbers. So why? again, with this liquid partition, it's simple. I say, well, something generates magnetic field for me, and then magnetic fields and cosmic rays are in dynamical balance in liquid partition, and then everybody's happy. Except people who
Well, I mean, to your question, I could consider it possible that it works locally, and I mean, in exactly the sense that he mentioned, that you have, if you create locally an overpressure in cosmic rays for some reason, because you have sources, then you have a possibility to open up either by thermal flows or by cosmic ray driven flows, whatever, and have a pressure release valve there. And that, of course, limits your cosmic ray number density here.
This is exactly why cosmic ray pressure can be much larger than magnetic.
So I would say you can have equilibrium locally on a local scale, but not on a larger scale, because that really depends on the dynamical evolution of the system.
On the other hand, if you look at the evolution of the supernova remnant with particle acceleration, it's not true that the supernova remnant evolves into a medium without cosmic rays. So it evolves into a medium with cosmic rays. So for a long time, even up to the Sigma phase, you don't see that the particles get accelerated, because due to the diffusion, everything is more or less wiped out. So you have to wait for large scale until you see an increase of the cosmic rays. So this is very different to that model we presented, because there is no cosmic ray explosions. Somehow yes, but they are rather smooth for a long time.
Yeah,
for large scale.
But the problem in the present, I made a simulation is that I should not apply such a high diffusion coefficient like the real one. I mean, with the realistic diffusion coefficient, cosmic rays immediately spread out. There is no even a spot of. So this is I observed it in simulations with a large diffusion coefficient, but I did not show them because they are relatively short.
Yeah, but this is. I think this is our basic question. I'm here in order to understand how important is cosmic ray for the galactic dynamo. And what I learned is that the gradient of the pressure is important. Yes, of the cosmic ray. If the cosmic ray is a large-scale phenomenon, then this pressure gradient, which is now extra in the momentum equation, is more important for the stratification or the structure of the galaxy. In order to produce helicity, this is the point. In order to produce helicity, it must be localized, like a supernova explosion or a superbubble explosion. This is my point. And so far, I forgot. Did you show some plots about the pressure of the cosmic ray? The scales or the distribution of the cosmic ray in your computation? I don't know. Is it a large? This is the point. Is it a large scale phenomenon or is it structured?
Depending on the diffusion coefficient. If the diffusion coefficient is realistic, then it is very large scale.
Yeah, then it has no influence to the density potential.
No, it has, because locally there are loops which start to rise due to the instability. So it is not, okay, on average the distribution is quite small, but there are regions which produce the
How big are they?
hundreds of parsecs.
Like supernova explosion.
But have you really seen that in the simulations? You did show us as the second picture a test where you had the flux tube. In the first test you had the flux tube and the diffusion was along the field lines. In the second test you allowed for the feedback.
Yes.
And the first thing that happened was that basically everything blew apart, except that you had a few supernova cosmic ray remnants, so to speak, at the ends of the tubes.
No, this was on the second plot. There was a gas, and the gas collected at the corners because of this pressure and the flow of gas along magnetic field lines. So, yeah, the explosion was at the center, and then two streams started to flow along the diagonal.
But it was,
Now I understand that the diffusion coefficient is important.
Yes.
And also it's anisotropic.
Yeah.
Otherwise, the pressure, the cosmic pressure. Yeah.
In this simulation, it was only 10%, but what I can say is that it works even better for the realistic one. However, the time of the simulation is much shorter than in the present one. So I just selected this one for presentation because it covers the whole cycle from the initial weak magnetic field up to the saturation.
But I have a question, when you say the realistic diffusion coefficient,
I mean,
what do you mean?
it
How
is
realistic?
something order of 6 times 10 to 28 centimeters square per second.
And that comes from?
It comes from the Andrew Strong
secondary to primary ratio.
Yeah.
Another question I have on the inspection of your nice plots here, or you showed it over them over in your presentation, is I have the feeling that there is a helicity or alpha effect only in rather far from the equator, so 200 parsecs or so, and there is no production of VR from B5. This is the alpha effect. This is the helicity. And in the layer around the equator, of course, I know that the alpha effect is zero at the equator. But in your results here, in the simulation, it seems as would the alpha effect start only in, say, 150 parsec. And then it changes sign. This is, of course, a preliminary analysis of the plots, and then it changes sign. So that my question is it possible that your structures, your explosions and cosmic ray pressure gradients are only existing far from the equator?
The width of the Gaussian profile of the cosmic of the supernova rate distribution as the Gaussian is the half width. The width is 100 pascals. So it is you mentioned 150, but it is something very close. So the supernovae are concentrated in the disk of fluster z equal to minus 100 up to z100. So, and I expect that this the effect of supernovae is just to expel the magnetic field from the nucleus.
Another argument is if you have a layer of supernova explosions, then always in the upper part of this layer helicity is positive, and in the lower part of the layer helicity is negative. This was in the first model of Katja Ferrier. She considered supernova explosions along the equator. And of course, the upper half of the explosions has a positive helicity, and the lower half has a negative helicity. So she produced positive helicity in the upper hemisphere of or plane of the galaxy, and negative helicity in the lower plane. But if you have a distribution of supernova explosions, then the average is important. This is the point. And so far, my question is, if I am correct that your alpha changes sign in, say, 350 parsec or so, is this a layer of explosions? Or do you have
there is a layer of explosions with the Gaussian profile in Z. Yeah. But on the other hand, Katarina will show alpha is highly fluctuating.
Beautiful, of course.
Yeah. In time and in space. Yeah. So it is not so easy just to compare the Z profile of alpha and Z profile of B.
Yeah, but this is a mean field.
Yeah, this is a mean field.
Yeah. I only speak about mean field calculations. Okay, we shall see what you present.
Well, half an hour's nearly. A few minutes left.
Second question.
I think that would be answered. Somebody said it is a dependence, but it's very weak, and nobody really argued against that. So maybe the last question, you asked the question at the end of your talk about this. I don't know if you want to answer now about the diffuse sources of ultra high energy.
But this was what
more time, but okay.
Yeah, so I usually say I distinguish first from continuous emission, not the emission. But I think if you see some spectrum that's peaked around some energy, that would be a very like a smoking gun for burst, because as you saw, even for rather small fields like a nanogauss, so you already have the effect that particles only arrive at a certain time with a certain energy. As soon as they are spread out over a larger time interval than the duration of the experiment, then usually they come all at the same energy if you have a bursting source. So if you see something like that, it's an indication for a bursting source, and at the same time that there are some magnetic fields between us and the source that are at least nanogauss or something like that, over, say, a couple of megaparsecs. I think that you can say that's fair enough.
But the burst was there maybe 1,000 years ago, right?
Yeah, of course.
So you just see a burst of cosmic rays, not cosmic rays.
Right, and in fact, that's an important point. It was always said that because some people speculated that you see a coincidence between cosmic rays and the gamma rays themselves. But that doesn't work because the delay time was already a few hundred years. So in fact, if you would see that coincidence, it would mean that the fields are much, in fact it would be more a hint against the gamma ray burst, because even in the galactic magnetic field, I think the delay time is already of that order of magnitude. So you would never see any coincidence. Because in the galactic magnetic field, you have a couple of microgauss over 10 kiloparsecs or so. And that alone gives you already a delay time of 100 years, so the remember correctly. So even if you have no, because it's quite, actually it's easy to calculate, because deflection is, in the galactic field, is about a degree or so. So now multiply, so a degree is a square of a degree, what is that, maybe 10⁻⁴ or so. You multiply 1 kiloparsec, which is 10 to the 4 years, where we get a year, but we have a bit more because it's 10 to the 4, there's 10 kiloparsecs.
Kiloparsec is 3,000 years.
Yeah, let's say 10 to the 4 years.
Yes.
Because it's a couple of kiloparsecs. And 1 degree squared is probably 10 to -3 or so. Right? I don't know, what is it in radians? I'm too tired now to
you shouldn't be.
Yeah.
1/3,000.
0.02 radians. So you square, you get 4 times 10 to -4. Now you multiply this 10 to the 4. It's a couple of years.
Mm-hmm. So you might expect maybe something. If something like that happens close by, you might expect that you should burst it.
But then as soon as you have just a little bit of extragalactic field, then you're on.
Yeah.
Then they have hundreds of years. So that's why I think that if you see monoenergetic spectrum, it will be a smoking gun for bursting sources.
May I ask a question? A short question. Yes, it was my individual ignorance. So there is no evidence for anisotropy in the arrival directions of ultra high energy.
At least not on our scale. Yeah. On small scale.
So these old results of the 80s and the 70s where people were discussing these anisotrophies very extensively, not just with better statistics than gone.
With which energies? I don't remember.
20s.
Well, at that time they had only, but even less, I think it was just the volcano range or something. They had, I think, one event around that. I don't even know that what volcano range was getting. I have no idea. But this is not discussed anymore because I think that the statistics is much lower than the last estimate.
So no evidence for any anisotropy.
No. But I said this small scale thing would have been that is important.
Anisotropy very high energies.
No, there is no anisotropy, statistically significant, number even was so small.
Right.
That there is no question of any anisotropy.
Okay, I think it's time to end And I'm sure I'm going to discuss the weather and not argue about science over the other way. Thank you.